So, characteristics. Yes, you got to know that about capacitors. Yes, you do. We can use Ohm's law and X sub C formula to figure out these parameters in this, what do we call it, series parallel capacitive circuit, right? Yes. So the first parameter we need to find, oh gee, C total, I'll ask you for that. What is it?
37.99.
That sound about right? They said 37.99 pico. What's the unit measure for capacitance? Farad. But what do we got to do first in this case to get that? Yeah, we have to, just like the series parallel inductor circuit, we have to find the equivalent now capacitance between C2 and C3. If you remember the rules, don't forget the rules. How do we combine capacitance in parallel? We add it! 16 pico plus 22 pico, a CEQ or equivalent capacitance of what? What's the answer? Now let's pick up with Valerius. Go. CEQ, what is it?
I got 38 picofarads.
38 picofarad. How'd that sound? Beautiful. So if we redraw our circuit, like highly recommended, 38 pico, and then we have that in series with the 0.25 pico from C1, we're just carrying over. Now we're dealing with the series circuit. What do we have to do in series? We have to reciprocate, so if we do that properly, we should come up with like 37.99 pico. Is it smaller than the smallest? Okay. Because if you were to take this 0.25 micro and you actually convert it to engineering notation, what is it? Yeah, like 250 nano? Yeah, like if you move the decimal, that's what I'm talking about. So far, so good? XC1, apply the formula. 402.5C, whoever's next, go. Salmon, XC1. Really? You're sitting there with your calculator? Hope not. Hope you did it.
I'll double check.
Okay, let's do it.
70.74 K ohms.
You said 70.74 K ohms. How does that sound? Pretty good or not? What? Let's see what I have for XC1 for this problem. I have those digits, but your engineering notation's off. Try it again. It's 1 over 2 pi FC. We're trying to find XC1. So 1 divided by 2 pi times this frequency of 9K hertz times 0.25 micro.
70.74 ohms.
There you go. That's right. 70.74 ohms. Good. There we go. All right. XC2. Let's do it.
I have 1.11 mega ohms.
Yeah. That's what I got. 1.11 mega ohms. Okay. Next. XC3.
803.81 K ohms for
Okay.
XC3.
That's what I got. 803.81 K ohms for XC3.
For XC2, I got 466.21 K ohms.
Close. Oh yeah, there. I'm looking at something else. Yeah. 466.21 K ohms. Now, how did you get that? 466.21. How'd you get that? XCEQ. How'd you get it? What do you have to do?
Take the difference between XC2 and XC2.
Really? No! How do we treat ohms in parallel? Because to get to XCEQ, it's XC2 and XC3, isn't it? How do we treat ohms in parallel? Not take the difference. Yeah, we know, but you got to say it right. Because if you say take the difference and I know what you mean and I'm just like, okay, because I know what he meant, and then someone else might not know what you meant, and then they take the difference on the test and get it wrong because of you. You know what I'm saying? So we got to make sure we say these things correctly. So we have to treat ohms like ohms in parallel and reciprocate. So by doing that, XC2, XC3, how many different ways can we reciprocate that? Reciprocate sum of reciprocals, what else can we do? Yeah, product over sum. Remember, there's 3 methods to reciprocate, so we can use 2. And if you want to be bare minimum, like Gauss, you only need to no product, or I mean, reciprocate some reciprocals, right?
Yes, sir.
Yeah, 'cause that works every time, no matter what. So there that is. The only thing left we gotta do is find I total. It's the only thing left I'm asking for, Ohm's law. What's the E we're gonna use there, Mr. Goff? What's the E? To find I total using Ohm's law, E. What E are we using?
25 volts.
Yeah, we're using boop. Yeah, because I'm asking for I total. Gotta use total voltage, that is, and the total ohms must be XC total, right?
Sir.
There it is. Where did it go? Dan, did we even find that?
We found it.
Oh, okay. I didn't ask for it. Right, I did, but I didn't write it down. What is XC total?
465.49 ohms.
465.49 ohms, sound good? XC total? Now we can find I total, yes! So there's the XC total, the totals. Total potential, total opposition, total current is, where was next? What is it? What is the answer? Oh, who's next? Then that Brown next? Hope you got the answer to this.
For I told for number 7.
Uh-huh. What? Ohm's law. Yes, see, look. I total. Yeah, XC total, because that is total opposition. You know what I'm saying? See? XC total, because it's just a capacitive circuit. So that is the total opposition. You know what I mean? So you take the 25 volts, which is the total potential, divided by the total opposition, Ohm's law. And I promise you, you will probably encounter at least one of these on the test tomorrow. Why give you practice? So we know how to do this stuff and we're ready to go. So what's the answer?
Oh, for I told for 7. 53.71 milliamps.
No. Try again. Your digits are right, your engineering notation's off again. Those of you who are still having notational problems, you need to pay attention when you're plugging these values in your calculator.
53.71 micro.
All right, 53 point, I got 6.2 micro, what, horses out in the field, what? 53.62 micro amps. Oops. Micro. Peek. Okay, so some of you need to get with it. Questions on series parallel capacitive circuit. So what could a possible question on the exam be? Given this series parallel capacitive circuit,
What is
XCEQ equals blank. Guess what you gotta do? You gotta go through and solve it to get to that part. Once you find the answer, you're done. Or if it's asking you for I total, well, guess what? You probably gotta solve the whole thing to get there. Don't be lazy. Don't be lazy. Now, if you're slick, hey, you can find C total. Hey, you can plug it up there and find XC total. Hey, you can take 25 volts divided by XC total and done, and not even have to find the individual capacitive reactances if you're slick like that. So keep that in mind too. Save yourself some time if you realize that.